Hi, how are you? Today let's study the birth of the universe, the Big Bang theory. Okay, the Big Bang theory explains the birth of the universe. First, let's start with the wave nature of light. Okay, the first question is, what is light? Okay, what is light? Now people know that light is both waves and particles. So if a bunch of light is coming to your eyes, then that is a bunch of waves. And it is also a bunch of particles. And each particle is called a photon. Okay, a photon. Okay. This is the family of the electromagnetic waves. Okay. Electromagnetic waves have long waves and short waves. I mean the wavelengths. So what is wavelengths? Wavelengths is the distance between two neighboring peaks. So this is a peak, right? This is also a peak, but they are neighboring, right? They are neighboring peaks. Okay, so this distance is called the wavelength. Okay, so this wavelength is long, right? And here the wavelength is very short, right? Okay, so wavelength is long here and wavelength is short here. Okay, so this is a family of electromagnetic waves. They have these family members. They have radio waves. Radio waves have long wavelengths. For example, more than 1 meter long. Okay, and then microwaves, right? Microwaves, you know what microwave is, right? In your kitchen, you have such a device. Okay, microwave. So the wavelengths must be as short as a few centimeters, right? A few centimeters. So these are microwaves. And then if the wavelength is as short as a few millimeters or micrometers, then such wavelengths are called infrared radiation. Infrared. Red, you know the color red, right? Infrared means outside or before or lower than, right? So infrared means outside or say before the red, right? And this is radiation, so infrared radiation. And then if the wavelength is, okay, this number you need to remember. If the wavelength is 700 nanometers, then the light is red light, so the color is red. And then if the wavelength is 50 nanometers shorter, so for example, that is 650 nanometers, then it is orange. And then another 50 nanometers shorter, then that is 600 nanometers, so that is yellow light. And then 550 nanometers, then that is green light. And then 500, then that is blue. Then 450, then that is indigo. Then 400, okay, so if the wavelength is 400 nanometers, then the light is purple light. Okay, purple is also called violet. Okay, violet. And then if the wavelength is shorter than 400 nanometers, then the light is ultraviolet radiation. Ultra means more than, right? More than, higher. So more than violet, more than purple. So it is ultraviolet. You know ultraviolet. When you were a small child, you heard of this thing. That is UV. Okay, UV ray. Of course, you know what UV ray is, right? UV ray. Okay, so the wavelengths of UV rays are shorter than 400 nanometers, right? So 400 is purple, 700 is red light. Remember, right? Okay, 400 and 700. 700 is red and 400 is purple or say violet. And less than, shorter than 400, UV ray. And shorter than that, then that is X-ray. And the shortest, of course, gamma ray. Okay. Okay, and then the shorter the wavelengths, the more powerful, we'll say, the individual photon has higher energy. Okay, because I said light is also a bunch of particles, right? Since a particle is called a photon. So the shorter the wavelengths, okay, the higher the energy of individual photons. Got it, right? So the higher, the shorter the wavelengths, okay, the more penetrative the radiation is. So gamma ray is very penetrative. It can penetrate the concrete worlds, okay, and X-ray can penetrate your bones, right? So you take pictures of your bones using X-rays. Got it, right? And UV ray can penetrate your skin, okay, and then the visible light can only penetrate the transparent stuff, right? Transparent stuff, okay, and so on. And visible light is already very weak. I mean, the energy is already very weak. Okay, remember that, right? So red light has, the individual photons of red light has weaker energy, right, than purple light. Got it, right? So purple light, the photons have higher energy than the photons of red light. Got it, right? Okay, so let's move on to see how light is produced. Okay, how light is produced? Then elements, chemical elements can produce light. So for example, hydrogen can produce such light. This is ultra violet, right? So UV ray. Okay, 4 different wavelengths. Yeah, 1, 2, 3, 4. 4 UV rays. Okay, look, the wavelength is shorter than 400 nanometers, right? Wavelengths. This is wavelengths. Okay, nanometers is the unit, nanometer. Okay, so shorter than 400 nanometers, right? Here for this because this is hydrogen, this is sodium, this is helium, neon, mercury. We now only pay attention to hydrogen. Pay attention to hydrogen only now. So hydrogen has 4 wavelengths, 4 different wavelengths of UV ray, right? And then 1 wavelength of purple light, right? And then a bunch of indigo light, right? And then a bunch of blue light, and then a bunch of orange light, right? This is orange, right? 700 is red, right? Okay, 400 is purple, and 700 is red. So this is orange. So now we remember this the light emitted by hydrogen. Okay, hydrogen only emit such light. So these lines, black lines. So the color of the light emitted by hydrogen is not black. Okay, the black lines are here just to show you that what kind of light hydrogen emits. UV ray, purple, right, and indigo, and blue, and orange, right? And sodium will emit only yellow light, right? And helium can emit indigo. No, this is not indigo, but blue, right? Yeah, this is indigo. Okay, indigo and blue light, right? And yellow light and orange light, right? And neon produces just yellow, orange, and such light, right? This is neon. Neon can produce such light. And mercury can only produce these wavelengths of light. Okay, so different substance, different elements produce different light, right? So such lines are like the fingerprints, of such elements, right? For example, humans, different individuals have different fingerprints, right? Then now the different elements produce different types of light, right? So actually this spectrum we call this spectrum. So this spectrum is a fingerprint of our hydrogen, right? And this is the fingerprint of sodium, and this is the fingerprint of helium, right? And this is the fingerprint of neon, and this is the fingerprint of mercury. Okay, if in your mixture you have a mixture of many different elements, then the light, okay, is continuous, right? So the light can be continuous, so be mixed. Any kind of wavelengths can be produced, right? Then the spectrum is continuous, like a rainbow, right? Like a rainbow, continuous rainbow, continuous color. Got it, right? Okay. But for one individual element, then there is a fingerprint here, right? Okay. Then let's see how light is produced. You studied in chemistry, the chemistry unit. Okay. For example, this is an element. So this is a hydrogen element. This is Niels Bohr's explanation. You know Niels Bohr, right? Who is Niels Bohr? You know the Rutherford Bohr, Rutherford Bohr diagram, right? For the elements, atoms. So for example, this is a Bohr-Rutherford diagram of what? Of hydrogen. Okay, this is the first shell of the electrons. The electrons are on shells, right? Hydrogen has just one shell, right? So this is the first shell. However, there may be imaginary shells, right? Because actually the other elements have many shells, right? So you can imagine that hydrogen can have many shells. So this is the first shell. Usually the electrons, the one electron, hydrogen has just one electron, right? The electron stays on this first shell. Okay, however, there are imaginary shells. For example, this is an outer shell, right? Another outer shell, another outer shell. So this is the first shell, n is equal to 1, n equal to 2, second shell, third shell, fourth shell, fifth, sixth, and then many shells, right? Okay, so the electron, if it absorbs light, photon, absorbs a photon, if the energy of the photon is exactly enough to jump to this one, then it absorbs some light and then it jumps to this second shell. And if it falls back to this first shell, when it falls back, then it produces this light. Okay, so what is light? Light is emitted when an electron drops from a higher, or say an outer shell into a inner shell, or say a higher energy level to a lower energy level, and the energy difference is exactly the energy of the photon, and the energy of the photon determines its wavelengths, right? I said the shorter the wavelengths, the higher the energy, the longer the wavelengths, the lower the energy, right? So this energy determines the wavelengths of the photon, and then this also determines the color of the light, right? Because I said the color is also wavelengths. For example, 700 nanometer wavelengths, then the color is red, and if the wavelength is 400 nanometer, then it is purple. Got it, right? If the wavelength is shorter than 400 nanometer, UV ray. Got it, right? Okay, so the energy determines the wavelengths, hence the what? The color. Got it, right? Okay, so because this energy is shorter than that one, right? Oh no, I mean energy is lower than the second one, right? So this second one has a higher energy. If, for example, a electron is first excited to this energy level, or say that this shell, the third shell, and then when it falls back onto its own original first shell, then this energy difference is equal to the energy of the photon, right? And then the energy determines its wavelengths. So that is the second one, the left one, the from the right to the left, right? The second one, okay? And then this is the third line, right? And then, yeah, it corresponds to this third line. And this fourth one corresponds to this fourth line, right? So these four jumps, 1, 2, 3, 4. These 4 jumps correspond to these 4 different wavelengths or 4 different colors of light, right? Emitted by hydrogen element. Got it, right? Okay. And then these 4, okay. This one from the third shell, it falls back to its second shell. Then this energy difference is changed into the surplus, the excessive energy, right? So the energy is released, so it is in the form of photon. So it emits a photon. So this photon, the energy of the photon is equal to this energy difference, right? Okay, you have already known that, right? This first shell has the lowest energy, you know, because a lowest place has a lowest energy, right? And the outer the shell, the higher the energy, right? So this is the low energy level. This is the second lowest energy level. The third lowest energy level. So the energy level is higher and higher, right? From a higher energy level, if you jump to a lower energy level, so there is excessive or say surplus energy, right? So the energy must be released. So in the form of a photon, right? So this means when this electron falls back from here to back to here, then there is a light emitted, right? There is a photon emitted. So this photon, the energy of the photon is short, right? I mean, in this family, or say brothers of 4, then this is the shortest. This has the lowest energy difference, right? Lowest energy difference, smallest energy difference. So the energy of this photon compared to the other 3 must be the smallest one, right? Since the energy is the smallest one, then the wavelength is the longest one, right? So this falling, or say this jump from higher to lower, this jump corresponds to this light, okay? This light. And then this second one corresponds to this light. Got it, right? And then this corresponds to this one. And this fourth one corresponds to this fourth one. Okay, so now I have explained the production, the production, or the making of these 8 different colors of the hydrogen emission. Got it, right? So these 4 correspond to these 4, and these 4 correspond to these 4. Okay, got it, right? As for those jump, now we don't care because the energy difference is too short. So this is infrared. Infrared radiation we cannot see, right? So it is not included in this visible light spectrum. Got it, right? Okay. So light is produced when what? When an electron falls from a higher energy level, or say a outer shell, back to a lower energy level, to a inner shell, then light is emitted. Got it, right? In the form of photon. Okay. And the photons have wavelengths, because the light is both photon and is both particles and waves. Got it, right? Okay. Okay, so now we come to our second topic, the Doppler effect. So this is about waves. So this is the wave source. So for example, if you are dipping on a very quiet lake. So for example, this is a basin of water, or say a lake of water, and you are dipping this center. Then this center is the source of the wave, right? So this is the source of the wave. And then you make waves, right? One cycle of wave, another cycle of wave. So the waves move from the center to every directions, right? To every directions, moving to every directions. So If you make a wave here, then you can see waves here, here, everywhere, right? And if you speak, then your sound is also wave. So for example, you are here, you speak, then people can hear you from here, right? People here can also hear you. 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 And people here can also hear you, right? And your sound, the quality of your sound is the same everywhere. How come? Because the wavelengths of your sound is equal everywhere, right? Is the same everywhere. Okay, the wavelengths. Okay, this is the sound waves, for example. So this is a circle is a wave, a peak of a wave, and the distance between a peak and another neighboring peak, then this is wavelengths, right? The wavelengths. So the wavelengths is the same everywhere, right? The wavelengths is equal everywhere. However, when you are moving, if you are moving, as you are moving, you speak, then this direction, people here can see shorter wavelengths, and the people behind you can see longer wavelengths. So if you sing as you walk, then people here can hear higher pitch, and people here can hear lower pitch. Or say the tone, your tone. Here you have a higher tone. Here you have a lower tone. I mean the people can hear. People can hear higher tone, and people here can hear a lower tone. Got it, right? Okay, so let's read these words. Okay, in a stationary source emits sound with a particular frequency. So what's a particular frequency? Or I say a particular wavelength. The frequency or the wavelengths is the same everywhere. However, in B, the source is moving to the right. Okay, when the source, this is the direction of the source. The source means, for example, you, when you are speaking, when you are singing, then the source of the sound is you. So when you are going to the right, okay, so the audience in front of you can hear higher pitch, which means shorter wavelengths, and people behind you can hear lower pitch, which means longer wavelengths, or say more coarse sound. Got it, right? Okay, we use another example. So for example, this is a fire truck, and the siren, when it is driving at a very fast speed, and it turns on the siren, then the audience in front of the truck hear very short wavelengths, or say high frequency. High frequency means the high pitch, so the sound is very sharp. And people, audience, or say audience behind the truck can hear long wavelengths, or say low frequency, or say low pitch, or say the sound is not sharp, that is coarse. Okay, got it, right? The universe consists of billions of what? Billions of galaxies, right? Galaxies. And if you can also use a telescope to watch each of the galaxies, right? And then you see the galaxies emit light, right? So the light comes to your telescope, right? However, the light actually changes, okay? So for example, originally, if you measure the light emitted by a certain element, then you see such 4 lines of color, or say 4 different wavelengths. So this is the fingerprint of a certain element, okay? The light emitted by a certain element in that galaxy. However, after some time, you measure it again, you observe the light again. Then you find that the light moved to the right side. Look, originally these four fingerprints are here, right? Closer to the yellow, okay? Closer to the yellow, further away from the red. But now after some time, you measure again, then this moved to the left side of the yellow, okay? Closer to this red, right? So this phenomenon is called red shift. Red shift. So red shift, what does it mean? What does it imply? It means that, right? It implies that the wavelength is becoming longer, right? Okay, so if the wavelength is becoming longer, what does it mean? So it, according to Doppler's effect, we know that, right? So it means the source, the light source is moving away from us, right? So if the light source is moving away from us, then what does it mean? Then it means we are in the process of a Big Bang, right? We are in the process of a Big Bang, because for example, if this is a galaxy, this is another galaxy. So if we are here and we observe the light from this galaxy, then during the process of this explosion, the distance between a certain galaxy and another one is longer and longer, right? The distance is longer and longer. Since the distance is longer and longer, then it appears that it is moving away from us, right? So it moves away from us, then its wavelength becomes longer, right? Okay, so the experiment, or say the observation, implies that we are in the process of a Big Bang. Okay, so this is the Big Bang theory. And since the objects are moving actually, if you observe all of the different galaxies, you can find that all of them have red shift. So this means all of the galaxies are moving away from us, right? So it is a Big Bang, right? And since this is a Big Bang, then originally there must be a starting point, right? So people can imagine that more than 10 billion years ago, actually 14 billion years ago, okay, the world was just a point, just the universe, the universe was just a point. Then all of a sudden, it explodes, bang! Then the Big Bang theory is that. So now we are still in the process of the Big Bang, because the other galaxies are still moving away from us. Got it, right? Okay, so this is the Big Bang theory. And some other experiments can also, or say other, not experiments, sorry, other observations can also support this theory. So what kind of observation? If you see this picture, in the future, for example, then you need to know that this. What does this mean? This means okay. Some technicians or engineers, they measured the microwaves. Okay, the microwaves radiation from the universe. Okay, they measured in all directions. The microwaves, microwave radiation from all the directions in the universe, the microwave radiations are the same intensity. So what does this mean? The microwave is not emitted by stars. If the microwave is emitted by stars, then if you face the disk of our Milky Way galaxy, then because there are more stars, right? Then you can see higher level of the microwave radiation, right? However, they tend into many different directions, but they receive the same amount of microwave radiation. So this means that the microwave radiation in the universe is still uniform. Okay, so the distribution of the microwave radiation is uniform in the universe. So what does this mean? So this means that the microwave radiation is actually the residual radiation of the Big Bang, or say that is the residual noise of the Big Bang. Got it, right? Okay, so this supports the Big Bang theory. Okay. So today let's just study so much. Okay. Thank you. Have a nice day. Bye.